just for posterity's sake here, just because this is such a classical calculus problem, where you try to fit a rectangle inside of a parabola and figure out what the maximum area can be for the rectangle. Now, the easy version of this problem is this one. This is the one I kind of got trumped on when I was working with Emily, and I hadn't done calculus in a while. And I couldn't figure out how to do this one, and yet this one is extremely simple, because the area of that rectangle is x times y. Excuse me, 2x times y. Right? If you consider that this measurement is x from here to here, then the base of that rectangle is 2x, and the height, well, this point is y.
That's right, that's right.
So the area of that rectangle is 2x times y, and if you have an equation for the parabola, then you substitute it for y. In other words, let's say the parabola is x minus x squared plus 2. Well, you substitute that in, and you have an area function that is a function of x only. Then you can differentiate it and figure out where you have a maximum. So this problem is like this problem, only...
Oh, wait, what did you substitute in for what?
Okay, let's say this parabola here,
yeah, the 2x plus y
by that.
Okay.
In other words, I put a minus sign because it's pointing down, and I moved it up 2 units. So I got minus x squared plus 2 for the equation of this parabola.
Okay.
So the area of the rectangle is 2x times minus x squared plus 2.
Oh, I see what you mean. Okay.
Now I have the area of the rectangle is minus 2x cubed plus 2x. Well, I can differentiate the area to figure out where it's the maximum and figure out what x makes that the maximum.
Okay, okay, I understand, yeah.
So, the only difference between this problem is figuring out what the base is. In other words, in my problem, the base was pretty easy. In other words, this is like talking about circles at the origin as opposed to circles that are not at the origin. Yeah. But in my problem, the formula for the parabola is quite simple, and the formula for the rectangle is even more simple. This is the x, that's x right there. That's y right there. So the area of that rectangle is 2x times y. And we know what y is in terms of x, so we can proceed from there.
Okay.
So let's figure out what the area of this thing is. They give us the area, or they give us the formula for the parabola. They start us off with y equals 2x minus x squared. So that's that parabola.
Okay.
What is the area? And I'm going to have to draw this because it's pretty tough to figure out, actually. The beginning of the solution figures is, what is that point there?
So you have to figure out the x-intercepts of that.
Right.
Function,
obviously, one of them is 0. What's the other?
One would be 0. Let's see, how do you figure out the x-intercept there? I can't remember that.
Set y equal to 0.
Oh, that's all. Yeah, okay.
Because the x-intercepts mean that y is equal to 0.
Right.
So if I solve this, factor that x out, I get setting that equal to 0, I get x is going to be 0 or x is going to be 2. So this point is 2. That's step 1. In other words, on the x-axis, that point is 2. So now, this next step is one actually quite common in calculus, but it's still very, very difficult to come up with. Figuring out what the base of this rectangle is. Remember, it can be like this.
Yeah, right. So it's still...
So how can I define that rectangle?
Let's see, 2 minus, I guess, how do you know?
Yeah, no, you're on the right track. You're on the right track.
You can figure out that the two slivers there, what those are.
Well, what are they? They're x. One of them is x. In other words, let's redraw the parabola that I just erased. If you let this be x,
okay.
Well, by symmetry, this is also x.
Okay.
In other words, I'm calling x the distance from here to there, the first corner of the rectangle. With me?
Yeah, so also...
So what's the base of that rectangle?
Okay, the base would be 2 minus 2x.
Yes. The height is y, right? In other words, that value there is y.
Because that seems like x we're using as an arbitrary...
Yes, that's
variable.
what's hard to understand about this. But if you think about it, this is a variable. We don't know that it's going to be right there. That's why I said we could draw this like this. Is all we know is that the base is some base, and I don't know what it is. So it's perfectly acceptable to use this distance as a variable, x, and call it x. Whatever.
So it's also just coincidentally on the x-axis, but it
Well,
could have been...
yeah. Well, that's not accidental. In other words, that's why we're calling it x. But
yeah,
this distance is x. In other words, when we come up with an answer, our answer, we need to know what x is. X might be a half, x might be an eighth, x might be 1. It could be anything. We don't know what it is. So we're going to call it x. But if we call this x, well, by symmetry, this is also x. And based on the fact that this is at 2, then the base of this rectangle is 2 minus 2x. And the area of that rectangle is its base, 2 minus 2x times its height, which is y, which is 2x minus x squared. Now we have an area function that is a function of x, and if we want to know where the area is a maximum, then I'm going to differentiate it, set it equal to 0, and solve for x. So let's do that. So the area function is equal to, let's see, 4x minus 2x squared minus 4x squared plus 2x cubed, which is, let's put it in order.
The whole technique, first we differentiate, then we do what?
No, first we multiply.
Oh, I see.
That's all I'm doing here, and I'm gathering like terms.
Okay.
So here is our area function, right here. The area of this rectangle is equal to this.
Okay.
Okay.
So we got.
So if I want to maximize my area function, I set it. I take the derivative. I want to take the first derivative of the area function, which is 6x squared minus 12x plus 4. And I set all of that equal to 0. Well, this is a quadratic. And just given by the answers I'm seeing, all of these answers are irrational numbers. So I know this thing probably doesn't factor.
I see.
I could divide everything by 2 to reduce it a little bit. So I get 3x squared minus 6x plus 2. And that still doesn't factor. I can tell it doesn't. 2 times 3 is 6, and you still have the other term you got to add into there. So there's no way that factors properly. So if I want to solve this, I get x equals minus b, which is 6, plus or minus the square root of b squared, minus 4 times 3 times 2, all divided by 6. In other words, using the quadratic formula, this becomes 6 plus or minus the square root of 12 all over 6. And this becomes 6 plus or minus, this is 4 times 3, so that's 2 root 3 all over 6. And now I can divide top and bottom by 2. So I get 3 plus or minus root 3 over 3. So I get 3 over 3 plus or minus root 3 over 3. Let me show you my phone's new capability. This is too cool. I've got to show it to you.
Okay.
Let me turn my camera on because I think I have to show it to you that way since I don't have any other way of doing it.
Okay. Yeah.
Okay, there's my new phone. Hold on. This has a capability on it that's amazing, really. Hold on. I got to figure out how to get it here. Okay, what is our problem here? Our problem is 1 plus root 3 over 3. Okay, hold on. See if you can see this. I'm not sure you'll be able to. 1 plus root 3 divided by 3 equals...
Oh, okay.
You see that?
I can't make out anything. But
Right, I don't see it either. Yeah, but all I did was I wrote with my little cursor,
stylus
with a stylus, and it translated my writing into numbers, and it's giving me 1.577. In other words, it gave me the answer. In other words, I put in 1 plus root 3 divided by 3, and it gave me 1.577. And if I put in 1 minus root 3 over 3 in script, I didn't like that one. I didn't write that one correct, so let's me back up. Hold on. I guess your handwriting has to be somewhat good. 1 minus root 3 over 3 equals 0.422. So, put my phone away. That's interesting that my camera couldn't read it because of the brightness. And let me turn my camera off. So we have two answers, which surprises me because I thought one of them would be negative.
Yeah.
And we'd be able to throw it out. No, 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 no. One of them can't be negative. Notice that both x's are positive. We have a 0.422 and a 1.577. So this distance right here has to be 0.422. That x right there. This.
Oh, I see. So you would add 0.422 and then plus 2 minus
Well, the base
1.577?
is 2 minus 2x. So the base is 2 minus 0.844, which is what? 1.156. There's the base. And we need to multiply it by the height. Which is 2x minus x squared. Seems like we could have two different answers here. Let's see, is the height ever negative? Yes, it is. No, it isn't. In other words, even if I put in this answer for x into this height, I get a positive number. And if I put in this answer for x into the height, I also get a positive number.
Oh, I see. Okay. So area was...
Is it the same number, perhaps? I'm not sure. Here, let me look at the answer here. This is 41.
Oh, no, it would be 0.422 each time, right? Because symmetrically...
They distinguish between x is less than 1. So the area of the rectangle as a function of x is 2 minus 2x times that. That's what we had.
Yeah.
Which is this. To compute the maximum, either plug directly into a calculator, definitely the faster option, or compute a zero of the derivative. That's what we did. One of the roots, 1 minus root 3 over 3. That's one of the roots, and plugging this into a is we get 0.777. So 0.770. That's the area.
Okay.
The other root corresponds to values of x greater than 1. In this case, our formula for the base produces a negative value. Oh, I didn't notice that. That's what I was kind of looking for. In other words, if we use the 1.156, how do we get a negative value? Notice that 2 minus 2x is negative if we use the other answer. In other words, that quadratic produced two answers for x, 0.422 and 1.156. But if we use the 1.156, the base becomes negative. 2 minus 2 times x becomes a negative number if x is 1.156. So we throw this one out. And the only x that works is 0.422. And when we plug in 0.422, we get an area of 0.770. So D, what is the maximum area possible for that rectangle? It's 0.770. Ooh, that's a good problem.
All right. That seems like a pretty good one.
Yeah. Yeah, it's a really good one because you come up with two positive solutions to your quadratic, and yet one of those positive solutions produces a negative base. And you obviously cannot have a negative base. So you would throw that one out.
Yep. Huh, okay. That was a good one.
Yeah. That really is, to me, a classical optimization problem for calculus, where you're optimizing the area of the rectangle. And you have to define the area as a function of x, and then you have to differentiate it, set it equal to 0, and solve for x. And we did that, but in this case we got two different values for x, but one of them produces a negative base, so you throw it out. Use the other one, and that area comes out to be 0.770.
I got it.
All right, that's probably a good place to stop.
All right.
41, yeah. All right, I'm not quite sure what we're going to do when we get to the end of these problems. We got about 10 more. I have some ideas, though.
Okay, sure.
Yeah, I do have some good ideas that I think you could probably use some review over some of those pre-calculus subjects we talked about.
Sure.
And there's also Chapter 10 of Calc BC that we need to review, at least first part of it. Oddly enough, I've been on the lookout for problems from Chapter 10 so we could skip them. And every problem we've come across from Chapter 10 is really the simple part of Chapter 10. It just has to do with the derivatives of parametric equations. And that's actually rather easy. We'll be able to cover that simply. But there's all kinds of difficulties. There's maybe one or two other questions, now that I think about it, where you have to find the area of polar graphs. That's a little tough. But so we can cover that. That'll keep us busy for quite some time, actually, doing all of that.
Wow.
All right. Timur, I will talk to you next time.
All right. Thanks much, Dave. We'll have a good one. We'll talk to you next. Have a good Christmas and everything. If I don't talk to you before.
You too. All right. Talk to you later.
Okay.
Bye-bye.